Good evening, both of you. I was 2 minutes late. Or I think we have to begin the class right now. I was thinking so many of you should have joined by now, but just two of you waiting for the class. So how was your day? Melody and Obawumi.
I think that this network is a good one.
I didn't hear you.
The network is a good physics class.
I can't even hear what you're saying. What did you say? Your network is bad, please. Hello, can you hear me?
Yes, sir.
Whose network is breaking? Okay, I want to believe everyone can hear me. Lucas, you're welcome to the class. Christine, you're welcome. Obawumi and Melody, can everyone hear me?
Yeah, good evening, sir.
Okay. So, where did we stop in the last class? Lucas, you were in the last class. Christine, you were in the last class. Melody also. Where did we stop in the last class, please? No one is saying anything.
Uses of X-rays.
Use of X-rays. Okay. Okay. All right. Okay, today I want us to look at an interesting aspect of physics that's part of the things you may likely expect even as you prepare for your SSCE, and that would be on dimension analysis. I will continue. There's a topic I need to do, and that will be our last topic even for this boot camp. That topic would be somewhat a continuation of the photoelectric effect we did in the last class. So I'll do that in our last class, and that may likely be the next class. I wouldn't know. Well, let's see how it goes. All right. Can you hear me?
Yes, sir.
Yes, sir.
Can everyone see my screen?
Yes, sir.
Yeah.
Okay. Okay, today we'll be looking at dimension analysis. Actually, I didn't include this topic in the curriculum I gave out that I'll be teaching for this class. But while I was having a class with one of you, like a student also preparing for SSCE, the student mentioned something on dimension analysis, and I feel there is a need for us to see how to tackle questions on dimension analysis using the basic things you already know in your SSCE. Now, you already know that we have quantities in physics we call fundamental quantities, and we also have derived quantities, right? Please, I would want you guys to respond. So I would be in tune that you guys are hearing what I'm saying. Can everyone hear me?
Yes, sir.
Okay,
Yes, sir.
said in physics, every quantity you have in physics can be divided into two. The first one is the fundamental quantities. The second is the derived quantities. All right. And I want to believe that everyone here already know what the fundamental and derived quantities are all about, right?
Yes, sir.
So what are fundamental quantities and what are derived quantities? Can anyone try? What are fundamental quantities and what are derived quantities? Just simple definition. I don't want to believe nobody can define fundamental and derived quantities. We'll just stay there until someone speaks.
Fundamental quantities are physical measurements.
How do you mean physical measurement?
Length and mass.
I said every quantity in physics are divided into two, and we have these are the two quantities we have: fundamental and derived quantities. And when we say fundamental quantities, what are fundamental quantities? That's the question. So if you say they are physical quantities, I don't really understand what that means. So you may do well to explain.
I only know the names of them, which are length and mass.
So how many fundamental quantities do we have?
I know length and mass are fundamental.
Is there only one person we have in this class? We have more than one person in this class. Why is the only one person responding? Seems if you guys don't like responding, so what will happen is that I will just teach, whether you understand it or not. I will just proceed because questions are being asked and just one person is talking. Please, that person playing that background song, can you do me a favor? Just mute your mic. So let's move on with the class. So in physics, we have two types of quantities. The first quantity is called the fundamental quantities, and the other is called the derived quantities. And what are fundamental quantities? Fundamental quantities are quantities in which every other quantity depends upon. So they are every quantity you can talk of depends on these quantities. We call such quantities fundamental. All right. So anytime you think about fundamental quantities or anytime you are discussing about fundamental quantities, just know that fundamental quantities are simply those quantities that every other quantities are dependent on. And that's what it is. Meanwhile, of course, derived quantities, as you already know, they are quantities that are obtained from the fundamental quantities. And that is just the simple difference between fundamental and derived quantities. Now, under these fundamental quantities, we have 7 fundamental quantities. So, fundamental quantities, we have fundamental, We have 7 fundamental quantities, and these 7 fundamental quantities include, this is 7 fundamental quantities. They include the length, the mass, the time, we have temperature. Let me write that upward. We have temperature, we have current, we have luminous intensity, or let me write amount first, and then we have the luminous intensity. These are the 7 fundamental quantities we have. And under these fundamental quantities, of course, length, the unit of length is meters. So length is measured in meters. Mass is measured in kilograms. Time is measured in seconds. Temperature is measured in Kelvin. Current is measured in amperes. Amount is measured in mole. And luminous intensity is measured in candela. So these are the 7 units of these 7 fundamental quantities. But under these 7 fundamental quantities, the first 3 quantities forms the basics of what we're going to be talking about today, which are the dimension analysis. So anytime you hear dimension analysis in physics, we have to consider the 3 basic fundamental quantities. The 3 most essential fundamental quantities are the building blocks for the dimension analysis. And these are the length, mass, and time. But before then, I want to believe that we know how to write out dimensions of every quantity. I want to believe we can write out the dimension of every quantity you can think about. All right, because by the time I give illustrations, we'll begin from the ones I believe you should already know. Then we should, before we go into the thing, the way you might expect the question, even as you prepare for your SSCE. So there are 3 principles. Let me write it like this. There are 3 principal fundamental quantities. Which are the mass, the length, and the time. These are the 3 principal fundamental quantities. Of course, you already know the unit for mass is kilogram, the unit for length is in meters, the unit for time is second. But what are their dimensions? The dimension for mass is capital letter M, the dimension for length is capital letter L, the dimension for time is capital letter T. So once we hear fundamental quantities, you should be able to, once you hear dimension analysis, you should be able to tell the the dimensions of these principal fundamental quantities, which are mass, length, and time. Because everything we'll be doing on dimension analysis will depend on these 3, just as you will see even as we proceed with examples. So take note that the dimension for mass is capital letter M, dimension for length is capital letter L, dimension for T, time is capital letter T. All right. So if I ask you something like, meanwhile, I've talked about fundamental quantities. I didn't mention derived quantity because you can only write the dimensions of derived quantities, even as you're going to see now. Because every example we'll be looking at, all of them will be principally based on derived quantities. I already mentioned that derived quantities are quantities obtained by combining 2 or more fundamental quantities, or by simple combination you may put of fundamental quantities. Those give us derived quantities. An example of derived quantities are the velocity, force, acceleration, momentum, moment, and the likes of that. And every of these quantities, you can write their dimension as long as you know how to write those quantities in their basic derivation format. For instance, if I have something like velocity, how do we define derived quantities? The first derived quantity I want to talk about is velocity. Now, if I may ask you as a class, how do we write velocity in terms of equation? Who can give me the equation for velocity from your elementary physics?
Displacement over time.
I didn't hear you.
Ten.
What is the derivation for velocity from your elementary physics? How do you derive velocity?
Displacement divided by time.
Thank you. Displacement divided by time. Now remember that displacement is distance in a specified direction. And if that be the case, it means that if you want to define length, you will tell us the length between 2 points. That's distance. Okay? The distance from point A to point B is simply the length between those 2 points. So it means that I can write the dimension. Of course, you know that displacement is measured in meters and time is measured in seconds. And have it in mind that anything that is measured in meters has the dimension of length. Remember, the unit for length is meters. So anything that has the unit meters has the dimension of length. Anything that has the unit kilograms has the dimension of mass. Anything that has the unit second has the dimension of time, which is capital letter T. All right. So you should be able to take note of these things. So if I want to write the dimension for velocity based on the fact that the derivation is displacement over time, it means that displacement is measured in meters. The dimension is going to be capital letter L divided by time is measured in seconds. The dimension for time is capital letter T. So I can then write this in initial form, which is LT minus 1. So this is the dimension for velocity. All right. So you can actually coin out their dimensions based on their derivation. So if you can derive these equations, you can write out what their dimensions would be. Another one, acceleration. I know I'm taking time to begin from here, so that by the time we get to start solving some simple y problems, it wouldn't be any issue at all. Acceleration. How do we define acceleration? Acceleration is simply velocity or change in velocity all over time taken. So acceleration is change in velocity all over time taken. And clearly, you've already seen that we already found the dimension for velocity, which is LT raised to power minus 1. So it means that I can write the dimension for acceleration as LT raised to power minus 1 divided by what? T, which is actually the time, velocity over time. And if I write this also in initial form, I'll be having LT. This T comes up, pick up a negative sign. So I have LT raised to power minus 2. And this is the dimension for acceleration. So as velocity, LT raised to power minus 1. Acceleration, LT raised to power minus 2. The next quantity also I want us to look at is force. I'm taking time to write out some of these dimension analysis. So some of these dimensions, so that when we start using them in solving applications, as you will see, it wouldn't be an issue. So I have force. How do we define force? Principally, force is simply mass multiplied by acceleration. And clearly from the last slide, you've already seen that I derive acceleration. The dimension is LT raised to power minus 2. So this is LT to the minus 2. And the dimension for mass is simply capital letter M. So if I multiply these two, the dimension for force becomes mLT raised to power minus 2. And that is the dimension analysis for force. The other one I want us to do, I'm taking time to write out formulas that are somewhat related. Then I'm having the other one to be what? Pressure. Let's say pressure. And how do I define pressure? Pressure is simply force all over area. That's the basic formula for pressure. And what is force? From what I did in the last one I did, that of the force, we already found that the dimension for force is mLT minus 2. So mLT minus 2 divided by area. Area is simply length times length. So length times length will give us area, which is L raised to power what? 2. And if I apply indices at this point, I'll be having mLT minus 1, L minus 2. Because once this L raised to power 2 comes up to the numerator, it picks up a negative index. And then indices, I have L raised to power 1 and L to the minus 2. So I'm going to apply simple law of indices, and I have that this becomes mL raised to power minus 1, T raised to power minus 1. And this is the dimension for pressure. So pressure is mL raised to power minus 1, T raised to power minus 1. The next one also, let's talk about maybe something like perhaps let's say momentum. Momentum. How do you define momentum? Momentum is simply mass times velocity. So mass times velocity. And what is mass? The dimension for mass is capital letter M. What dimension for velocity? LT raised to power minus 1. And this becomes MLT minus 1. So this is the dimension for momentum. So I can go ahead and write out many quantities and their dimensions. And I want to believe that every one of you should have mastered how to do this, even from your elementary physics. But before we proceed, I want you guys to try out this one. Write out the dimension for the following quantities. So I have a drill here. Write out. If I don't need to write the equation, you can already hear me. Write out the dimension of the following quantities. I have quantities like moment. I have something like let's talk about density. That person making attempts to talk, have it in mind that I can't even hear what you're saying. Moment. The other one is density. We can talk about quantities like impulse. Impulse. Let's say quantities like work done. Work done. Let's say quantities like what other quantity? Let's make it 5. Moment, density, impulse, work done. Someone should help me with one quantity so I can make it 5. So you tell me the dimension for each and every one of them, even as you try them all yourself. Moment, density, impulse, work done. Let's say quantities like power. Let's use power. Okay. So what you do for me right now is to tell me the dimensions for each of these quantities so that we can proceed with the real deal for the class. So what are the dimensions for those quantities? I don't know why you guys are not responding. You guys are not being responsive. Lucas, okay, there are 5 quantities here. You guys are 5 right here. I'll be asking you people one after the other. Lucas David, Goldin, Obaumi, Winner, Melody, and then Christine. So 5 of you, you are going to tell me the dimensions for each of those quantities. Lucas, you tell me the dimension for power. Melody dimension, you tell me the dimension for density. Christine, you tell me the dimension for work. Obaomi, you will tell me the dimension for density. Then Goldin, you will tell me the dimension for impulse. So let's look at it one more time, even as I ask you of this dimension, the dimensions for these quantities.
Okay. Oh, sorry. Now the screen, I can't see the screen. Maybe it's my network. So you said the dimension for power.
Please, can you according to the screen?
Yeah, maybe it's my network. My one is coming on and off. I don't know.
But can you see it now?
No, it's still just showing C. Then later it has turned on now. Later it might still turn off.
Wait, are you seeing it now? You're not seeing it. Let me know.
Yeah, I'm seeing it now.
Okay. So I say you're going to tell me the dimension for power.
Power.
Yes.
M1 M1 L M raised to power 1, then L raised to power 2, then T raised to power minus 3.
Next person. About me.
Yeah, the screen has gone off now. Maybe it's my network. I don't know.
I think it's a network because
Yeah.
I'm not that fine with the screen. Is there only one person that knows that understands how to write dimension for basic physical quantities?
For the impulse is MLT raised to power minus 1.
MLT raised to power minus 1. Okay. I'm waiting for other 3 persons.
For work done, ML to the power of 2, T to the power of minus 2.
ML to the power of 2, T to the power of minus 2. Okay. We have 2 more persons. Who is taking the moment? We have moment and density. We've answered that of the power. Moments, if you are confused, is simply force multiplied by distance. And if you're careful enough, you know that moment has the same dimension with work done. Because in work done also, this is force multiplied by displacement. So F times Z is your work done, and F times Z is also your moment. All right. And then if the dimension for what is force is simply MLT minus 2 multiplying distance, which has dimension of L. So this will give us ML to the 2, T minus 2. And that's exactly what she has answered. So both work done and moment has the same dimension analysis. All right. Now, what about the density? The person with the density. How do we write density? Density is simply mass all over volume. So anytime we talk about the density of a substance, we are talking about the ratio of the mass of the body divided by the volume of that body. And what is the unit for mass? The dimension for mass is capital letter M, volume, L raised to power 3, which is L times L times L for a regular object like your cube. The volume of a cube is L raised to power 3. And if I put that into test, applying indices, I'll be having the dimension for density to be ML raised to power minus 3. So everyone, many persons, and if not all of you, should be able to tackle simple questions like this involving dimension analysis. Where there might be little problem is when the question is being given via applications. So you see, they will give you question on application of this dimension analysis, and you'll be asked to solve the relationship between certain quantities and another quantity. Example, look at this question now. Question, let's look at examples. The velocity of a particle undergoing motion on a string or undergoing simple harmonic motion depends on the tension on the spring, depends on the tension of the spring and the mass per unit length on the tension of the spring, let's call it capital letter T, and the mass per unit length let's call that rho. The question now say, determine the relationship between these quantities using the method of dimension analysis. Okay, you may do well to write down the question even as we prepare to solve it. They say the velocity of a particle undergoing simple harmonic motion depends on the tension on the spring, T, and the mass per unit length, rho, of course, of that very spring. Now they say we should determine the relationship between the velocity, determine the relationship between these quantities using the method of dimension analysis. So before I solve this question, how many persons can solve this? Let's even know what we are doing. How many persons should be able can write the relationship for those physical quantities? You may just do well to put up your hand. Let's understand that you've okay, no hand is up. That's fine. So it means it's important to learn it. So take down the question first. Write down the question before we can proceed into solving the solution. Okay. Having written down the question, let's go straight into solving it. Solution. Actually, one of the applications of dimension analysis is that we use them to verify relationship between quantities. All right. So anytime you have a quantity, it's just like you have, many of you should have come across this formula in your simple harmonic motion, that T equals what? 2 pi root L all over G. All right. So many persons should have come across this formula dealing with simple harmonic motion. I can ask you to use dimension analysis and show me this thing, to show this thing now. So if I say that the tension of an object, the tension of a particle undergoing simple harmonic motion depends on the length L and the acceleration due to gravity G, and I ask you to derive this equation, you should be able to derive it. And maybe we'll do that in the next question. But before that, let's do the one we have given already before we can look at that. Now, the question clearly stated that the velocity of a particle, V, depends on, let me go back to the question. The velocity of a particle undergoing simple harmonic motion depends on the tension and the mass per unit length. So, the first thing I had there is velocity. I write it out. It depends on the tension and the mass per unit length. So mass per unit length is simply mass divided by length. So it depends on velocity. What is the dimension for velocity? Lt minus 1. Tension is a force, and every force has the same dimension. Tension is simply force on a string. So whether on a string or anywhere, force is force every time. All right. So the dimension for tension is simply the dimension for force, which is mLt to the minus 2. Of course, mass is capital letter M, but because I'm having mass per unit length, I'll be having mL to the minus 1, which is mass divided by length. All right. So these are the dimensions they gave me. But from the question says that the velocity V depends on the tension T and the mass per unit length rho. So velocity V depends on the tension T and the mass per unit length rho. And of course, you know, in mathematics, anytime you are giving proportionality sign and you want to remove it and bring in a constant, all right? But if you want to remove it, you need to bring in a constant. So this implies if the velocity depends on T and rho, it implies that V must be equal to what? K, T, and rho, where this K is simply a dimensionless constant. It can be anything, okay? So usually we assume it to be 1 when solving problems, or we just ignore it. And at the end of the exercise, we bring in what K is, because K is simply a constant, all right? So having known this, but for us to prove the relationship, we need to understand, we need to assign powers to these variables that are dependent on V. Remember, V depends on T. I can call this place X. I can call this place Y. My job would be to find the X and Y. Once I find the X and Y, that would give me the relationship between these two, between these variables. All right. So if I remove the proportionality sign, this symbol here, and I brought in my equality sign, I'm now having that V equals KT rho, but the X is still there for the T, and rho has to have the symbol Y. So it means that I can ignore K, since A is just a dimensionless constant. So I can ignore K and put in the parameters for these very quantities. So my velocity has a dimension of Lt to the minus 1. My what's it called now, tension has a dimension for what? mLt minus 2, which is a force, and then the rho, which is mass per unit length. So everything here is raised to power x, all right? And then the mass per unit length is going to be ml to the minus 1. Everything here is raised to power y. So my job will now be to, of course, let me take off the bracket sign. We've applied the law of indices there. the power multiplication law, I have that this will give me the dimension mx, L to the x, then t to the minus 2x. And for this one, I'm having m to the y, then L to the minus y. So all this thing here is equal to LT minus 1. All right. The next thing I'm going to do will be to merge up the like terms. So m appear twice there. That will give me m raised to power x plus y, because in indices, if they have the same base, then you're going to add up the powers. So the bases are m, I pick one base, the powers are x and y, I simply multiply, I simply add up the powers. I'm sorry about that. I simply add up the powers, which is x plus y. All right. Now L appears twice also. I pick my L here. I'm having this to be x minus y, and T appears just once there. So I write down the T minus 2x. So those are the things I have after applying the laws of indices. The next thing I'm going to do would be, remember everything here is equal to LT raised to power minus 1. And clearly, if LT raised to power minus 1 equals that, I can choose to multiply the left hand side of this equation by 1. Of course, if you multiply something by 1, it doesn't change the equation at all. All right. So if I multiply LT raised to power minus 1 by 1, it will still give me LT raised to power minus 1. But I want to write that 1 in a special way so that it will aid me to solve this problem right here. Remember that m raised to power 0, anything raised to power 0 is 1. So m raised to power 0 is going to be equal to 1. Why am I introducing m raised to power 0 here? Because in this my right hand side, I have m, I have L, I have t. But the quantity they gave us on the left is only L and t that it has. So I need to look for a way to bring in m to the left, which will simply be by multiplying by m raised to power what? 0, which is a beautiful one. All right. So I have m raised to power 0 here to make up for this equation. I can now compare powers. Comparing powers. Comparing powers. If I compare powers right here, let me write in the next slide. I'm going to compare m, the things in m. If I compare m, on the right, I have x plus y, that's the power here. On the left, I have 0. So x plus y is equal to 0. That's the first comparison I'm going to have. So I have that if I compare power. So for m, my observation is that x plus y is equal to 0. The next one we have, if I compare the power for the L, clearly I'll be seeing that if I compare for the L, where is it again? If I compare for the L, I have that x minus y is equals to 1, because the power of L here at the right, without the power is 1. You should know that. So x minus y is equals to 1, and the last one, minus 2, is equals to minus 1. So those are the parameters we have. So second one is x minus y equals to 1. Third one is a minus 2. So that's minus z, right? Okay, minus 2x, that's what we have here. So minus 2x is going to be equal to minus 1. All right. So if I compare the power, if I compare that of the y, that of the L, I have that x minus y is equals to 1. Then if I compare that of the t, I have that minus 2x, right? Is that minus 2x or just 2x? Minus 2x equals minus 1. So minus 2x equals minus 1. So I'm going to write out these things as equations, right? And solve them simultaneously. So setting up the simultaneous equation. Setting simultaneous equation. That's my SE. So the first equation is that x plus y equals to 0. That's equation 1. I have that x minus y is equals to minus 1. That's equation 2. Sorry, is equals to 1. That's my equation 2. Is equals to 1. And then I have that minus 2x is equal to minus 1. So I can call this one equation 1. I can call this equation 2. I can call this equation 3. So clearly from equation 3, I already know what x would be. So from equation 3, my x is simply going to be 1 over 2. Because I'll be having that minus 2x equals to minus 1. Divide both sides by minus 2x. That will give me that x is 1 all over 2. So having found x, I can put x into any of the equations to find to find the value of y. So x is half from equation 3. So put x equals half into, let's say, equation 1. Equation 1 says that x plus y is equal to 0. So this means that x, which is 1 over 2, plus y equals to 0. So my y becomes minus 1 over 2. So my y clearly there, y is going to be minus half, because 0 minus half is minus half. So I found the value of x and y. So I'll simply go and put them back into that general equation where v is equal to kt raised to power x rho raised to power y. So if I do that, having found my x and y, so putting the value of x, and y into, let's call that equation star. So I can go and number it equation star. Sorry. So let me call it equation star. This equation star right here. If I put the value of x and y into the equation, what I'll be having is that v is equals to k t. Remember, t raised to power x, and x is what, half. Then L, that's rho raised to power y, and y is simply minus half. All right. So if I apply the law of indices right here, firstly, I can even choose to factor out the half, but this will give me kt rho to the minus 1, everything here to the power of half on the outside. So this will give me that k. If I apply indices here, I have tension all over rho, that everything there is raised to power half. So I can call that my square root, because anything raised to power half means the square root of that thing. So firstly, I apply indices. Indices gave me that other than writing t rho raised to minus 1, I can write it as t all over rho. And since I have everything raised to power half, I can then change the half power half towards square root. So k is not affected by the half. That's why you see that the k is outside the square root. So the velocity relationship is such that v is equal to a constant multiplying the square root of t all over rho, where rho is simply the mass per unit length. Any question? Does anyone have a question? Sometimes it's quite
No,
unfortunate that students are in class and things are being taught. Some persons wouldn't understand and they won't ask questions. I don't know why you find it difficult to ask questions, because as a student, if you must know something, you must be a good student of asking questions. You shouldn't but ask your teachers questions. And it shows that if you don't have a question, it shows that you guys don't prepare for any class, or you're not even prepared for the exam. Because if my calculations are right, YX should be coming up in short while. That's next month. With the month is almost up, that's the month we are in right now. So you should be more ready than you've ever been. You have many topics you've been taught so far from your year, from your first day in SS1 till the final day, till your exam. It means that you are familiar with almost all the topics as long as physics is concerned that you should know. And just in case you don't, you still have to read up and learn to ask questions. If I ask you now, yeah, how many persons understood what we did? Let me see your hand up. If you understood the principle, the step, and how I got to that V is equal to K root T all over rho. Let me see your hand up. You see, no hand is up because obviously maybe you missed one or two things. Now I have a question. How you didn't understand a particular thing? Please ask. Let me go back to the board. There's something you don't understand. Please, you can ask your question right now. This is where the solution all started. This one, this is class 3, okay? There's a question right here. So ask your question. No one is asking anything. I don't. You don't understand all, but you were here when I was doing everything. You didn't say anything. All true. Now, ask your question. Who you about me? I think you understood everything we did. Can you please explain to me how we got the value of x? How did we get x? It's actually a burden to teach. You know, this class is not a physical class. It's online class. Well, if I'm the only one talking, responses are not forthcoming. I don't even know whether you're there because everyone is mute. Everyone's faces is not everyone's faces is not being seen. I can't see you. I don't know what you're doing. You're not asking any question. So there's nothing interesting to just teach and no one is saying anything. You don't understand it to your network. Christine, what's your own? What's your own challenge? Do you understand?
No, sir.
You don't understand still. Lucas, do you understand? Lucas, I asked, I said, do you understand? Melody, do you understand?
No, sir.
From what point are you lost, Christine? From what point are you lost?
I didn't understand the question.
Let's go back to the question. Here comes the question. The question says that the velocity of a particle undergoing simple harmonic motion depends on the tension of the spring T and the mass per unit length rho. The mass per unit length of that string, of course, that is what the question is saying. That we should determine the relationship between the quantity between these quantities using the method of dimension analysis. So this is actually this between these quantities using the method of dimension analysis. This is just the question. All they want us to do is that we should use dimension analysis and write the exact relationship of this statement. And what's the statement? That V depends on T and rho. And that's what I did here. First of all, I have to write out the dimension for velocity, which is LT raised to power minus 1. Tension, the dimension is as the same thing as force, because tension is simply force on a string. All right. So I wrote out the dimension still, which is MLT raised to power minus 2. And of course, mass per unit length simply means mass over length. And if that be the case, I wrote out the dimension also to be what? ML raised to power minus 1. M is mass, L is length. So these are their dimensions, ML raised to power minus 1. From the question says that the velocity V depends on the tension and the what? Mass per unit length. This is how to interpret this question. This is how to interpret it. That the velocity, if I say that K or K depends on P, that K depends on P and M, or K varies directly as P and M. What I'm trying to say is that K varies P and M. And if I want to find the relationship of K alongside P and M, I need to attach a power. I can use X and Y, A and B, or whatsoever thing. My goal will be to find the powers, those powers I'm introducing. If I can find what they are using dimensional analysis, that gives me the exact relationship of those quantities. But they said that V varies what? T and rho. That's what we have there. Now, I quickly introduce, after writing the equation, but we assume that, of course, not assumption, anytime you want to remove the symbol of proportionality, you need to bring in a constant, and I call that constant K. K can be anything. K can be pi, K can be 2 pi, K can be 3 pi, K can be 1, K can be anything. Just having in mind that K is just a dimensionless constant, and you don't have problem, you don't have any issue with solving the dimensionless constant. You only keep it constant and then solve other things, okay? You don't make use of it, just solve for the variables that were given to you in the question. So I took out the proportionality sign and I brought in the equality sign. I have that V equals K T raised to power X and rho raised to power Y. All right. And from here, we already know that V, the dimension for V is LT raised to power minus 1. The dimension for tension is MLT raised to power minus 2. Of course, tension has capital letter X, sorry, has power X. That's how I have this power X there. Then dimension for P, for rho, is ML raised to power minus 1, and rho has the power Y. That's why the power Y is there. You see, I didn't touch the K. I just left the K the way it is. I want to solve for X and Y. That's what I'm after. So I didn't carry the K along. But at the end of this expression, I'll still put back the K at the letter end. So if I apply indices here by expanding this power, this bracket using the power, this X here is going to come for the M. So I have M to the X, I have L to the X, I have T to the minus 2X. That's for the first one. And here I have M to the Y, I have L to the minus Y, because Y, when this Y opens up the power here, this is exactly what I'm going to have. All right, from here, I apply indices. M appear twice here, which is this and this. And according to indices, when the bases are the same, you take one of the bases and then add up the powers, as provided the powers are the variables are multiplying each other. So M to the S multiply M to the Y is going to give me M raised to power X plus Y. That's what I have there. L to the X multiplying L to the minus Y. That will give me that L raised to power X minus Y. And of course, T doesn't have anything to multiply with. I brought down the T raised to power minus 2X. All right. The next thing I would do would be to compare the powers. I need to compare the powers. by comparing powers is to check, remember, how did I bring in this M naught here? I check that on my right hand side I have M, L, and T. But on the left I have only L and T. So I need to multiply by 1 to make everything balance. So I have M, L, and T on both sides of this equation. All right. Remember, anything multiplied by 0 is 1. So M raised to the power 0 doesn't necessarily change the nature of what the equation is giving. But why did I bring it up? I want to compare. If I compare M on the right is x plus y, M on the left is 0. So I will write that x plus y is equal to 0. That's the first comparison when I'm dealing with M. When I'm comparing L to the right is simply x minus y, and L on the left is positive 1. So I can write that is it positive 1? Yes. So I can write that x minus y equals 1. That is the second equation. And then the third one, t has power 2x minus 2x there, and t has power minus 1 there. I can equally compare that minus 2x equals minus 1. That is how I got these equations right here. So when I compare the M, I have that x plus y equals 0. When I compare L, I have that x minus y equals 1. When I compare T, I have that minus 2x equals minus 1. So if I set up the simultaneous equation, that's what I wrote by what I meant by SE. I have that x plus y equals to 0, equation 1. X minus y equals to 1, equation 2. And minus 2x equals minus 1, equation number 3. And clearly, from equation 3, you could see that x can be obtained as half. By dividing equation 3 by minus 2, I will get that x equals half. So having found x, the next thing I will do is to put the value of x into any of the equations, x equation 1 or 2, to find the value of y. And when I did so, I got that y, 1 over 2 plus y equals to 0. By the time I put that x into equation 1, and then if you make y stop that, y is equal to minus half. All right. So having found x and y, the next thing will now be to put the value of x and y into that general equation. We call it equation star. And equation star states that v is equal to k t raised to the power x rho raised to the power y. And clearly, x is half. That's why you saw me wrote k t raised to the power half. And then rho is simply y, and y is minus, sorry, the power of rho is y, and y there is simply minus half. That's why you see me writing rho, or you saw that I wrote rho raised to the power minus half. And then if I apply indices at this point, I have half and half. I can factor it out. I'll be left with t raised to the power 1 and rho raised to the power what? Minus 1. And if I write this thing as a fraction, I'll be having t all over rho. That's what that thing will give me. If I use a fraction, I have t all over rho. And then t all over rho, everything all to the half. And then if I change the half to square root sign, I'll be having that v is equals to k root t all over rho. All right, that's a simple application of dimension analysis. You may go back and also check and cross-check how much you can engage problems on this. But the second thing I want us to do would be to prove this relationship. Let's try to check whether this is true, that t, I want to prove this equation, that t is equals to 2 pi root L all over G. Let's see whether we can prove it. All right, let's start. You can see that the parameters here are what? T is actually what? Period. You have to understand what this whole parameters is all about. T here talks about what? Period. G here talks about acceleration due to gravity. L here talks about what? Length. All right. So let's see how we can engage ourselves and see what this whole thing would be. And then solution. I want to prove this, please. So just know that T depends on L and G. Let's see whether that works. So if I see T depends on L and G, I can say that the period of a pendulum bob depends on the length and the what? Acceleration due to what? Gravity. So LG. All right. So clearly, I can have that. If I remove the proportionality sign and bring in my constant, I have that T is equals to 2L. I'll add up the power X and then G add up the power Y. Please, there should be power here, X and Y, because those are the things that we're going to look for to set up our equation. All right. Now, what are their dimensions? Let's write out the dimension of these quantities. Period has a dimension of capital letter T also, because period is measured in second, and anything that has unit of second has dimension for second. And L is measured in lengths, but it has the dimension of what? Capital letter L. And G has the dimension of what? LT to the power of minus 2. So these are the dimension, the properties I have. So it means that if I substitute into this equation, period T dimension is equals to K, and then L raised to the power X, and then of course I have LT minus 2 raised to the power Y. So this is exactly what we have here. So I replace L, the length, with the dimension for length, which is L, and then replace G with the dimension, which is LT raised to the power minus 2, and I left the powers all the way they are. I can keep that K constant. Let's work with this first. I'll be under this is L raised to the power X, this is L to the Y, then T to the minus 2Y. All right. Everything here is equal to the period T. And then since I'm having L and T on both on the right hand side, I need to bring in L also on the left hand side here, but that would be L to the 0, because anything raised to the power 0 is 1, so that I can compare the sides evenly. All right. And if I try to do that, I have that comparing powers. Before then, applying indices, this is L T raised to the power 1, which is what I have there. The L raised to the power 0, T raised to the power 1 is equals to L raised to the power X. I have L raised to the power X, L raised to the power Y. I can multiply. That gives me L raised to the power X plus Y. According to your law of indices, then this other one is what? T raised to the power minus 2Y. All right. Now, if I compare these two equations, comparing sides or comparing powers, comparing sides, if I compare the L, which is the first one I have there, I'll be having that X plus Y is equal to 0, because that's what the powers are. If I compare the T, I'll be having that minus 2Y is equals to 1. And clearly, these are the equations. This one I can call it equation 1. I can call this one equation 2. And now from equation 2, we can find Y easily. So from equation 2, I have that Y is clearly equals to minus half. So I found what Y is. And having found what the value of Y is, I can put back Y into equation 1 to find X. So if I put the value of Y, put Y equals half into equation 1, equation 1 says that X plus Y, so X plus Y, so X plus minus half, X plus minus half equals to 0. So which means X minus half equals to 0. So clearly X becomes 1 over 2. So X is equally half. Now I have found X and Y. I have to now put back the value of X and Y into the general expression here. Look at the expression. Let me call it equation star. All right. So let's put the value of X and Y into equation star. So put the values, put X equals half and Y equals minus half into equation star. I'm sorry. And if I do that, equation star says that the period T is equal to K L raised to power X, which is L raised to power half, and then what again is there? G raised to power minus half. You see that? Because G raised to power minus half, the acceleration due to gravity. I can write this in indices form. This becomes K bracket LG. This is LG to the minus 1 before I put the what? LG to the minus half before I put the fraction 1 all over 2. So this is 1 all over 2 on the outside right there. Of course, if I write this thing in fraction form, this will give me K L all over what? G. Everything raised to power 1 over 2. And if I change that 1 over 2 to square root, I'll be having that K square root of L all over G. And that gives me that period is equal to K root L all over G. So if where K is a constant, of course, K is equal to 2 pi, which is a constant. It implies that the relationship T is equal to 2 pi root L all over G. And that was how we obtained. You see that we started from this equation right here. Look at what they gave us. I started from this thing right here, and I was able to prove that equation with dimension analysis. This was what I use here. And I could prove what the formula looked like because I understood dimension analysis. And this is the formula that T is equals to 2 pi root L over G. And I've been able to prove it clearly. No more argument that T is equals to 2 pi root L all over G. This is K here, K. Okay. Any question, please? Any question? No one is asking a question. Okay. If you're not asking a question that I did, if you don't understand, you can always do well to go back and check the videos. And the way you guys have been silent this night, I think that might just be the last question we'll solve for this class. So every other thing you can do well to check out for yourself and always learn how to ask questions, not just in this class, but in every class you may attend. It is very, very, very important. At this junction, I think I may have to allow you guys be. The class is so dull, and there's no point bombarding you with so many things when you don't have responses. See you in the next class, and have a good night rest.